Okay, so welcome everyone to the Yale Center for Research Computing. It's great to see some familiar faces, some that I've met at the faculty orientation recently. Today is the first XSEDE workshop that we're having on how to write grant proposals for XSEDE, and it should be another fantastic workshop. If you haven't heard about the other workshops that we've had at the center, you can find those at research.computing.yale.edu/training, and that'll give the list of workshops and also provide a space for you to sign up to get additional notifications about the workshops. Just a bit more about the Center for Research Computing. This is a new center on campus. It's 1 year old, and the two faculty co-directors of the center are Harlan Krumholz, a cardiologist who also is the director of the Center for Outcomes Research at the medical school and the Yale New Haven Hospital, and Daisuke Nagai, who's an astrophysicist who works in astronomy and astrophysics. The center itself focuses in really two main areas, providing support for both computational and data-intensive techniques. The areas of focus thus far have been on cyber infrastructure, so acquiring and running the HPC infrastructure, working with ITS on storage solutions for faculty and staff on campus. We've been providing a lot of high-end support, so direct working with some of the research scientists that we have within the center. And then these workshops, which we host on a fairly regular basis, and again, you can find those on the website. And finally, we are involved in some community engagements, which includes some regional grants as well as infrastructure grants, both with the NSF and the NIH. With that, I'd like to turn it over to Sohrab Ismail-Beigi, who is a great speaker and has had a lot of success with writing grant proposals for XSEDE resources.
Thank you, Kieran. Whether I'm a good speaker is to be determined. I've never given a talk on this before. We all give scientific talks in our discipline. All right, so I'm Sohrab. My office is in Beckton. That's across from that fancy graveyard. I'm in applied physics. That's my primary appointment, but I have also appointments in physics and materials science and engineering. So I'm here to tell you about XSEDE from my point of view, like what does it mean and how do I get it and what does that even mean? All right. So this is the outline of the talk. There's 4 parts. They're not equally long. First is about who am I and why am I here? And I have to tell you a little bit about what I do so you get a feeling of why the proposals are written that way. You'll have to, if you want to write one, you should think about what your domain of work is and how much time you need. What is XSEDE and the types of requests? That's the word they use for grants. All right. What does it look like? And what's a typical outcome? All right, so who am I and why am I here and what do I do? Okay, so I'm a physicist. I do theoretical computational physics. Probably like all of you, we do computation of some variety. I study how electrons behave in solid materials and at the level of individual atoms and electrons. So here, for example, we have some oxides of metals. Those are oxygens, nickel, lanthanum, nickel, and then there's titanium here. So there's something happening at this interface. And here I show you the result, computed result of an electron distribution. All right. So how do you find this? Well, you have to solve some partial differential equations. That's quantum mechanics. And because the atoms could be anywhere and there's nothing particularly symmetric about this, you have to do it numerically. So, this would have been obtained, the data you see here is smooth, but it would have been obtained on a grid of, say, 60 by 300 by 70 or something. So a big box of data, and you have to compute that. And the types of things you do are linear algebra, matrix diagonalization, and Fourier transforms numerically. Okay, so that's what I do for a living. So why am I here talking to you? One possible reason is that my group uses high-speed parallel computation for research, but so do all of you. The second reason is that we use the Yale HPC a lot, but probably so do you. So the real reason I'm here is because I've been requesting and using XSEDE since 2009. Okay? Also with the predecessor, but I wasn't a PI on those requests. So I'm only summarizing the time that I've been a PI on these requests. Right? And before that, I was using it as part of someone else's allocation. So what is it I do in my group in terms of the computational aspects? And this will explain a little bit about what we're asking for. Okay? Now, There's many different kinds of computations happening on campus. This is only one kind. For example, I don't do data-intensive computation. I don't need to. My files are at most a gigabyte or two. But I spend an awful long time generating that gigabyte of data, all right? So primarily, we're using open source software. Sometimes we write it ourselves, but mostly it's been previously written because the field has matured over 20 years and no one can write one of these by themselves now. There's too many bells and whistles that you have to write. Most of them are in this wonderful thing called Fortran 90, because that's, for some reason, scientific code is written in that reason for historical reasons, and that's the suffering we have to deal with. We only use very few standard libraries. FFT libraries, this is probably the best one around that's public. Basic linear algebra, and LAPACK is a linear algebra package. Sometimes we use the parallel version called ScalaPack. Okay, these are all standard, nothing fancy, all open source. Okay, a typical production job that a student or a postdoc would run would use 10 to 100 processors. You could use more and it would run faster, but it wouldn't scale well. Do you understand what I mean by that? Like if I go from 1 to 2 processors, I see pretty much speed up of 2. And then 2 to 4 is speed up of 2. For the size of calculations we happen to run on today's computers with today's infrastructure of communication between the processors, it peters out around 100. So, from a practical viewpoint, you'd rather run 2 calculations separately slowly than 1 fast, because it's not a factor of 2 anymore. Okay? Each job is a single MPI parallel instance. So it's not that we have 100 processors doing 100 different things and at the end they report to each other. They really communicate data and compute and communicate repeatedly during the entire run. So you cannot run a part of it. You have to run the whole thing. We run many, many such calculations on a material and its variants, like we'll move an atom, we'll swap an atom, we'll replace this thing by that thing, we'll take this atom away. So these are not a few huge calculations to just get 1 or 2 important numbers. Rather, we run enormous numbers of smaller calculations to get relationships between numbers and then to understand something about what makes an electron tick in some material. And the variants are generally human generated. So somebody will run 5 or 6 calculations, stare at the results for half a day, and figure out what to do next. We burn through between 7 to 10 million CPU hours a year for the whole group. We have a grant now that just one of the people would use 100 million hours, but that's on a separate category. You can't get that through a regular XSEDE grant, okay? But typically, people doing research in the group use something on this order. Okay, that's what we do. So group-wide, about 75% of that, 8 million hours is at Yale, and around 25% is at XSEDE for my group in the last few years. This is a running average. So you'd say, well, why are you using XSEDE at all, right? You can just run everything in Yale. Okay, well, extra CPU time never hurt anybody. The XSEDE supercomputers are large compared to the Yale clusters. So the queue times are quite short. And because they have extremely strict accounting for the hours you get, people just don't run stuff. They think carefully before they submit a job. So actually the queues are short. Okay, like you submit a job for a 100 processor, it runs within an hour or 2. Which compared to current, how busy say Omega is, that's very useful to have that resource. So think of it as something extremely predictable and quick, of which you have a limited amount. So we think carefully in the group about who gets to use how much of it for what. If you have to run like 1 million calculations and trying to figure out what's going on, we would say don't run it on XSEDE. But if you've done that already and you figured out the 8 calculations that you need to run for the next 3 weeks because the paper at the conference is due in 3 weeks, we give you the XSEDE time. Because you're going to be able to do it in a week. And then, of course, you'll make some mistake, so you have a second week to fix the mistakes, right? That's what we tend to use it in our group. They're at least as fast as the Yale HPC. It depends on which computer you're on and how old it is. And the support is very good. I'm not saying the Yale HPC support is not good. They are very good. They tend to be a little bit overburdened, helping everybody on campus. Here they have a large number of people just for that computer, only helping people for that computer. And they will work with you digitally over emails or whatever it is, many, many iterations to try to get your problem solved. This is a big computer center and they have really dedicated people. Okay, they're very reliable in the sense that we have essentially no unannounced downtime on the workhorse XSEDE machines. There are other machines that NSF runs that are more like cutting edge and they go down a lot without any explanation. Okay, so that's who I am and what I do and roughly like the universe I live in computationally and the scale of resources I use. So what is this XSEDE? And what is it for? So it used to be called TeraGrid until a few years ago, and then they changed the name. They added more things to it, but it's basically the same thing. So it's a network of NSF-funded supercomputers where the word supercomputer should be understood in a very generic fashion. It is officially centered at NCSA, which is an organization at the University of Illinois Urbana-Champaign. Okay? That's their headquarters. And then they have a lot of member groups, universities and supercomputing centers. So the big players that you may have heard of, University of Texas at Austin with their supercomputing center, University of Illinois itself again, Ohio State, and then the Pittsburgh and San Diego supercomputers that used to be under a different directorate and organization than they got into XSEDE. All right, and there's more. There's a long list of these, Purdue and all these places. So some of the computers are completely dedicated for XSEDE, and some of them, say at the university sites, they give 60 or 50 or 70% of the time to XSEDE, and the rest is for local computing. So there they have a fund, the NSF paid for part of the computer, and then the campus paid for part of the computer. And together they got to get something larger. What do they have? They have like everything you could possibly imagine. So they got regular HPC clusters, to run calculations of the kind I like. Sometimes they have GPUs, and sometimes they have large memory, and they've got lots of different things. They have GPU dedicated clusters, large ones. If you want to do high throughput, embarrassingly parallel, they have a cluster or two for that. If you want to do visualization, they've got a cluster for that. If you have really large data you want to store, they've got a network of things for that. If you want to do complicated file management and moving data around on a grid, they have that. Okay? They have all these things. I cannot tell you too much about these ones because I've never used them. I can only tell you about these ones up here. Right? But I'm just giving you the kinds of resources they have. So that's the caveat here. I can only really competently tell you about number crunching on XSEDE. Okay, so when you go to xsede.org, you land there, and you click on the button that says resources, and you can see what they have here. Right? And they can tell you about their software, HPC, H-throughput storage, networking, blah, blah, blah. Right? And you can click on those and learn of what they have. So for example, here's the top of the list of the computing supercomputers. Right? There's something called Stampede and something called Comet at San Diego. This is at UT Austin. Xstream is at Stanford. This is at Louisiana State University, Pittsburgh, Indiana, whatever. Okay? Different kinds of computers. Some of them are being phased out in about a year. Some of them, they don't know when they're getting phased out. They're not going to tell you yet. If you click on, for example, Stampede, you can see that, okay, it's a something power edge cluster, Xeon Phi, blah, 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 only 102,000 cores. And okay, so these are about an order to 2 orders of magnitude larger than computers we have at Yale. They're not a million times larger, between 10 to 100 times larger. And this is a big computer that they have. Many of them are smaller than this. Okay, so how do you get time on it? You have to put in a request for an allocation. There are 4 kinds of allocations. I've sorted them by some method. All right? Trial, startup, education, and research. These are the CPU hours, order of magnitude, CPU hours you can get with these kinds of allocations. Okay? There's an asterisk here. We'll get to it in a minute. The trial allocation is really very little computing time. It's just for you to get your feet wet and try your code and see if it even runs. They'll give it to you within a day or two. They'll give you 1K or 2K or 5K or something like that. Okay? Very fast. And you have it for 6 months. So you can use 1,000 CPU hours over 6 months. Okay? The main idea is to get your feet wet, get your code compiled, see if you can get any timings. You may run out of time. That's okay. You can transition to a startup, which is a few tens of thousands of hours over a year, okay? And they decide this relatively quickly, within a week or two, and they usually say yes. And if they say no, it's because they want some additional information or something like this, all right? That is really, the function of this is not to do science, because you'd be hard-pressed to do, some of us would be hard-pressed to do science with that, but to really make sure things are running and get data, which I'll tell you in a minute what data you need. Get real data on performance of your software. Education is really strictly for classes, but they're quite generous on short periods with giving a lot of computer time for people to run parallel computation classes. But you have to write a justification, explain the class, have the syllabus and stuff like this. But they can help you there. And it's around a few thousand hours per student per project in your class, whatever that means. I couldn't figure out what that means. But we're talking thousands of hours per student. So they can run a big parallel calculation for like, 10 minutes or 1 minute or a few seconds, depending how large it is, and learn about parallel computation. And this is the real workhorse, are these research grants. Typically, they start on the low hundreds of thousands, although I've seen smaller. Technically, there's no upper limit, which I found very odd. But in practice, if you start asking for more than 20 million, they probably won't give it to you. They'll cut you off and say, you should ask for one of these big computer grants, which have fancy names or funny names. So NSF has something called a PRAC, which at NCSA at Illinois has a Blue Gene supercomputer. They call it Blue Waters. And you can ask for time on that. You have to write a standard NSF 15-page grant with your CV and support and blah, 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 blah. And then you can get 100 million to 800 million hours or something like that. And they need to see documentation very clearly of the code's performance, that it scales to 20,000 processors or something, okay? So if you ask for a lot of time, don't expect you're going to get it. But if you're in the few millions to maybe up to about 10 million, they will consider it very seriously, and then they'll probably cut you. But, okay, so that's more or less the ballpark of grants that you see as standard research grants. If you look at what they fund, you don't see 100 million hours under the research category. Okay, there's quarterly submission windows 4 times a year. And then it lasts 1 year. So they got people on a rolling system so they don't go completely crazy in December with everybody applying. They split it into basically 4 stacks. Okay? These are the kinds of allocations. So really easy entry up here, and this one requires some work. And the some work is what I'm going to describe. If you want to get one of those easy ones, it's actually really easy. The main point here is this XSEDE suitable for your needs, and can you get some timing and parallel data if it is useful for your needs to get a bigger grant. Then you submit a research proposal after you've done that, okay? The research proposal must have timing and scaling data. I show it to you. About 5 years ago, it was optional but highly recommended, but now it is required. They will throw your grant out if you don't have this kind of section on it, okay? So and actually, they make you get a startup allocation before you get a research allocation. That's the official rule. They probably bend it once in a while, but it is the official rule. But the good news is, let's say you're doing your startup and you got all the data on month 2. You don't have to wait a year. You can just apply for the research proposal right then. And they'll just fold it over. Okay? So what does it look like to write one of these requests? Okay? Again, the education and startup are very short and very easy. Assuming you know what you want to propose, it should take you 45 minutes to do it. Okay? You write who you are and where you are, and then if you have grants supporting your data, you enter the information in the program manager. This always takes me the longest time. I have to go look up their emails and phone numbers and put it in. Then you have to write an abstract of your research. It's not very long. It's like a third of a page at 12-point font. You stick in your standard 2-page NSF CV, and then, of course, you have to decide which computer you want and how much time you want. And then you enter the text boxes, you hit submit, and then within a week or 2, somebody will say something to you, and usually they'll give you the time. Then you can get your login and read the manuals of how to use that computer. Very easy to do. So let's say you do that, and now you want to do the real thing for millions of hours. Okay, so it is in some ways like a standard NSF research grant, but it is less painful. Okay? Although there is some pain involved. It's not completely trivial. You cannot do this in an afternoon in front of a terminal typing in the little text box. Your chances of succeeding will be very low. Okay, so like any grant that has multiple pieces to it, okay, the main text is probably where you'll spend most of your time, and they really want NSF style, 1-inch margins or some minimum font size, blah, 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 okay? And it's 10 pages or 15 pages, I'll get to that. You have to justify the research and the plan and why you need the request, and if you have other computer support, they want to hear about that. Then you have to have a mandatory section about performance and scaling, maximum of 5 pages, your CV. And if you're renewing, you need to have a 3-page progress report on what did you do last year with all the time we gave you, and what publications resulted from that. Okay? It's all very standard, nothing special. And I will show you examples of all of these from my own proposal. Okay? You need 10 pages max if you're asking for less than 10 million, 15 pages if you're asking for greater than 10 million. It's an interesting system they have. Okay? All right, so what is inside the main text? So the reviewers will look at the main text. That's where they'll spend all their time looking at what you wrote and deciding what they think about it. So you should spend time on that. You have to get 3 things across. One is the research you're doing important? Now, it's very difficult to justify this broadly because some people do astrophysics and some people are studying viruses and another guy's making a transistor, right? So you must argue the importance of it in some sense of general scientific understanding or technology, whatever is appropriate to your field. But you have to do it. Then you have to say, like, what are the questions you want to answer and how, with some detail. This is not a real science grant that you have to go into the nitty-gritty with millions of references, but you have to make an effort. And I'll show you an example. All right? And then you have to say, I need 1 million hours to do this project because, and it has to make sense. Okay? We literally have 3 sections in our grant, as you'll see. So we write a section describing our research projects and why do you care. Then we have another section for each research project we say what we want to do. And then we have a third section in which we say we need this many hours because of blah, 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 blah. And I'll show you examples of that. Okay, so let me show you the PDF for this to see what it looks like. The other reason for doing it that way is that it's modular. So each student and postdoc can write their own section. Okay, so we're going to page quickly through it and then zoom in on some sections, all right? All right, so there's your abstract, right? There's your introduction saying the wonders of what we do is so wonderful and the world will be a better place. Then I have these sections where I say, oh, if we study epitaxial oxide semiconductor interfaces, this is important because, you know, transistors run the world, and then there's these materials and people are trying to make new transistors and blah, blah, blah. And we have a section for each kind of thing. I'll show you one is more zoomed in so you get a feeling. Okay? We happen to have, I think, 7 or 8 little projects that people proposed within the group. Okay? Then we say, okay, so that's why it's important. And then the next section is, well, what do you want to do? So this guy wants to study something called barium titanate on top of germanium, and he's going to do this to learn about that. But this is science still. But it describes this, how you're going to answer the questions you wanted to answer scientifically. Like if we run a calculation like this, then we can learn about that. So we do that for every project. Again, this document is not something you write once, but you can completely split it into pieces and have different people work on it, and then just assemble it at the end. And have good spell checkers. So that's how we do it. We make a little thing like, you propose you want to work on bacteria, then please write 1 paragraph saying why we care about bacteria. 1 paragraph saying how you're going to study the bacterial problems that are important computationally. And then 1 paragraph saying how many hours do you need. And you do that, and you do that, and you do that, and then we have it in a shared directory, and we slap it together. There's your proposal. Okay, then requested resources. So this person who was doing the germanium and whatever needed this many hours because this and this, and he had to run 25 calculations. Each one's costing 10,000, and blah, 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 blah. And then he came up with a number. All the numbers are very round, as you notice. There's never... And the reviewers don't mind that at all. They want to see round numbers. If they see like 27,126 hours, it's like really, okay? And then we summarize it. We wanted a total of 2.28 million. You will see a bigger version of this. And then I describe the local computing environment. And then I describe the other supercomputing support that we may or may not have. These are optional sections. We all have local computing support, so you should write something there. We've got our laptops, and then we get access to Yale's clusters, and they give us this much. Typically, we use this much. Let me see where we're going next. So that's a quick walking through. So let's read one of these very carefully. Why did we do this? Why did we study rare earth nickelate oxides, whatever those are? These are oxides of nickel. So recently some guys have been talking about these new kinds of transistors, and they function because of the change of resistance of a material. Oh, these perovskites also do that. And so that's a good thing. If we could understand something about these materials, we may be able to make new kinds of transistors. To this end, we need to elucidate the precise dependence of the crystal magnetic structure of these materials on applied strain. It's pretty high level, but hopefully this will convince your reviewer that we should care about the science. And you put in here whatever is appropriate to your field. Like, why should we fund this science with this supercomputing time? Again, the second one is like, how are you going to answer the question? Okay, so we want to answer about this nickel oxide and that nickel oxide and that one for this thing. And first we have to benchmark our theoretical apparatus where we have to, look at this parameter in the model, which has to do with nickel and oxygen. And after we did the benchmarking, then we're going to investigate strain by taking this material and that material and some of those guys and learn about how the band gap depends on strain and whatever. So that's what we're going to do. And then in the third thing, we say literally what we're going to do. For each system, we'll consider these kinds of models, and for these one, the parameter will be here with 3 values, blah, blah, blah. Okay, it will require 96,000 hours. How do we come up with that? We need 2 of these calculations times 3 of those and 16 of those, and we actually timed this. I mean, we have previous XSEDE grants, so when we time things, we were doing it within the startup, within the research allocation. But if you have a startup, you time 1 or 2 of them and come up with a reasonable number, and put that in your performance section, which I'll show you. Okay? Some of these numbers have been rounded up, and you should always round them up, but don't do it egregiously. Okay? The reason we round out primarily in our group is because people make mistakes. It really does take 1,000 hours to run this calculation. It really takes like 400, but since you're going to make a mistake the first time and then the thing's not going to converge the second time, finally the third time it's going to run. All right, so then we looked at the first 10 pages of this. Let's look at the scaling and performance, this required section. Okay, there's no uniform way to write this. Your maximum is 5 pages. What they want to see is a little bit of a description of what the software does for their own edification. Okay? Because if you need very strange libraries that they don't support, the reviewers will have to think about how much effort is it for the XSEDE to specifically enable your project, right? Or if you have some kind of very funky commercial package that costs a lot, they want to know about that. So in my case, we describe basically the physics in terms of applied mathematics. We solve these differential equations, we have these kinds of expansions, blah, 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 but with some references. Here's some data. For example, we took a reasonable size calculation that was representative. We ran it with different numbers of processors, the total CPU time, and then the speed up. We analyzed the data. This is called an Amdahl analysis, where it's the time normalized to, say, 1 processor versus 1 over the number of processors. Asymptotically, it's a straight line. This is a good way to do an analysis, because this is what they really care about. Let me zoom in on this equation. Okay, so let's say you run a bunch of calculations, right? And you get a bunch of data. This is a standard analysis from applied computer science called Amdahl analysis. The total time, we're going to split it into a serial part and a parallel part, which are defined via this equation. The serial part is constant, and the parallel part gets divided by the number of processors. Right? So if you had infinite number of processors, it would take the amount of serial time. So what does that mean, serial time? You have a big parallel calculation running. At some point, different pieces of them have to talk to each other. Right? It's not completely separate calculations. So communication has overhead, and then sometimes you have to sum a bunch of numbers, so you have to just wait for that to happen and redistribute those numbers back. These are all serial parts. You cannot parallelize that. That would go in here. So it says if you plot the total computing time versus 1 over the number of processors, in principle, in the asymptotic limit, you should be able to see a straight line. We have 2 different software packages here. They're completely different calculations within what I do. One of them scales much better than the other one. Okay? That's the data. The circles are the data, and the circles are the data, and here's a straight line. So what's really interesting here is to see where the intercept is. That is, an infinite number of processors, what fraction of your code is serial. If it's 1%, then when you get to 100 processors, you will run out of steam. If it's 1 out of 1,000,000, then you can really go up to 1,000,000 processors and scale very well. They care about scaling a lot because they can measure that. Performance is a different thing. This particular calculation scales beautifully. It's an enormous calculation of lots of things, and it scales wonderfully. I mean, it's like 0.001% is serial, but it's actually a very inefficient calculation. But that's very hard to measure, right? Like, maybe your algorithm sucks. I mean, it'll do the job, but it's really dumb, right? They can't judge that as easily. And how would one judge that, right? You would have to have 2 different algorithms solving the same problem and compare them, and most people don't do that. Okay? But you need to provide data either like this or something of this ilk, or maybe just a table, right? So they get a feeling for, like, where are you, right? I mean, if you're planning to run on 100 nodes, because that's what you wrote in your proposal, do you scale to 100 nodes? Are we really wasting time giving it to you? You should be running at 10 nodes. That's the kind of question they want to answer. And have you done due diligence? Do you understand your software? I would say that is the thing that is very important, to have some kind of data of this variety in this section. It doesn't have to be 5 pages. It could be 1.5 pages. And it doesn't have to have 7 different systems you studied. Just one representative system. Of course, the more you do it, the better it is, right? Once you do one of these, it's easy to do the next one. You're like, oh yeah, okay, we'll just run it with this many processors, make a plot. Okay. And it also tells you, the omdodal analysis, like, how much do you want to spend effort parallelizing your software? If your serial segment is 10% of the total, maybe you want to spend more effort parallelizing it. 1%, are you happy with that? 0.1%, it gets progressively harder to parallelize things. You run out of things after a while, right? And fundamentally, time to solution, right? I could spend 3 months parallelizing this to get it from 100 processors to 200 processors, right? Or I could just run 2 calculations at 100 processors and get my work done. These are practical considerations, okay? Okay. So you have to provide some data here. This is a required section. So they're serious about this. It's required, and they look at the results, but it's not the end of the world, okay? All you got to do is benchmark it. You can benchmark it on a computer that's equivalent to theirs, sort of. They're okay with that. You don't have to literally run it on theirs. They really prefer, though, that you get the startup allocation and run it on one of their supercomputers. It is not required that you show perfect performance. The first time we had it, our data looked kind of crummy. It was okay. They were okay with that. They suggested, in our case, because we weren't too bad, they suggested we talk about to the XSEDE specialist, see if we can improve it. It just happened that the next version of the software that was public source that was released was better. So we didn't need to do that. But the reviewers sometimes recommend that you say, please talk to X, Y, and Z to set up a collaboration for free. XSEDE scientists will collaborate with you to improve the performance of your code or whatever it is. I mean, within reason. But they have such resources, and you can get that as part of the grant for free. All right? So if you have bad performance, it's not the end of the world. Just discuss it. Say, well, I think I can fix it because of da-da-da, and the next version will do blah, blah, blah. And actually, we would like to get some help from XSEDE to do this. You can write this all in there. It's perfectly valid. But you have to have something. Okay. So there's a PDF. There's some references. I can show it to you quickly. Yes. Oh, we had a third scaling calculation. There it is. Okay. References. This is our progress report, the 3-page. Okay, so we describe what we did last year. Most of this work was published. Some of it wasn't. But it's like the rest of the report. You have to kind of say what you did. We tend to like to put as many pictures as we can, but this year we only had 1 because people were verbose. These are the publications that resulted that were indirectly or directly supported by XSEDE. Our acknowledgements always have XSEDE and Yale HPC because we actually use both sets of resources for almost all the publications. In their acknowledgements, we don't say how much of which one we used because that's embarrassing to both parties probably, right? Mostly to them because they're like, oh, you only use 1% of it for this paper, okay. All right, then you have your CV. This is my CV. It's a 2-page NSF CV, and that's pretty much it. Okay, these are the parts of the proposal. You'll spend most of your time on the main text and the performance, right? I believe you have either a copy of this PDF or you're getting a copy of this PDF so you can look through it and get a feeling for what it is. Let's see what else I can tell you. Okay. All right, so we finished that. Now let's see what the typical outcome is, just so we're on the real axis, right? All this sounds wonderful. All right, so we submitted to this one. For historical reasons, we're in this submission window in my group because somebody in the beginning submitted to that, so it's every year. So around mid-October, we're all running around frenzy. So how did we do this? We happened to start around September 15th. I definitely start a month earlier if you have a moderate to large group because people forget and then they don't know this and blah, blah, blah. So everybody started writing their paragraphs and I have people check on each other's paragraphs. And then write the next thing, and then write the next thing, put it together, then you read it, it doesn't make any sense, you ask them to write it again or By October 10th, we were in the proofreading stage. We're not working 24 hours a day on this, right? We're doing our research, and an hour a day or half an hour a day, everybody writes their text. And I prod them every week saying, where's your text? Oh, yeah. Okay. So by October 10th, we're proofreading, and we submitted it on October 15th. We should have done it on the 14th, but this year was the 15th. Okay, and then within 2 months, they told us. It was before the start date of January 1, so it was okay. They said, you're approved. What does that mean? So this is the current cycle. And we applied in 2015 for 2016. We asked for 2.28 million. Here's our comments. We need scalable LAPAC, FFDW, C, C++, Python, Perl, whatever. Okay. The reviewers recommended 2.28 million, and we got 1.61 million. You also have to ask for storage, but we sort of make up those numbers. And the reviewers thought 700 was too much for us, so we need 500 gigabytes. There was no logic either on our end or their end. Okay, we just needed enough storage to store our stuff. 500 is fine. Okay, this is a 30% cut. It is similar but slightly higher than previous years, which were closer to 20% for my group. I don't have access to everybody. Okay, why the cut? The reviewers are actually enthusiastic. They said give them all the time. So this came at the next level. When the panel finished his work and gave their recommendation to the program manager did something. They were oversubscribed. There's too many researchers and not enough computers, and the computers are never big enough. The total number of service units, that's CPU hours, requested was a factor of 3 times larger than available on all the systems. Okay? So the reductions up to 50% were imposed on some that were recommended. So first they cut a whole bunch of people, then they shaved everybody's hair a bit. You won't get what you ask for, and I don't think it works like this, that if you ask for 5 million, they'll cut it 30%. So you should have asked for 8 million, right? It doesn't work like that. They'll cut you down to what they think is reasonable. But probably it's true. If you ask for more, you'll get more. Just remember, if you ask for a lot, they're going to be a lot more strict looking at your proposal. Okay, so we're actually quite happy with this because it's a good chunk of CPU time. It lets us do some of our work in a predictable manner if we're on a deadline or we just need to get something done. Or it's a really large calculation. Sometimes we have to run calculations with 500 processors once in a while. And that's hard to obtain at the Yale clusters, but here it's not a big deal. And frankly, of course, we are very privileged at Yale, right? I mean, Yale has a lot of money, and the provost's office is spending money on free hardware for us to use. So, I don't know how other people at other schools deal with that, right? I mean, I can always fall back on Yale HPC. So this year we used 20% on XSEDE. Next year we use 30%. It's okay. So NSF, this is the NSF's XSEDE supercomputing architecture. Requesting time is sort of like an NSF grant. It's a lot easier than a standard NSF grant, but it's a little bit painful. It's free, so you really cannot complain too much, right? You'll get cut probably somewhere between 20 and 30%. Statistically speaking. And depending on your needs, it could be a lifesaver, it could be your workhorse, it could be padding, it could be extra candy. It depends on your computational needs. So for us, it's somewhere between padding and workhorse. And I imagine there's some people, especially at small universities, that don't have local infrastructure. It's their computer time that they completely depend on. And for some people, it's sort of like, yeah, okay, well, I'll use 1 million hours to, scratch my head. All right? That's it. Now, you must have questions, right? So if you have any questions, please ask. Yes?
So what is the duration for a research proposal that we have to spend our computational time?
You have 1 year.
Within 1 year.
Within 1 year.
Even for a startup as well?
Officially, a startup is 1 year. Officially. At any time during a startup, you can put in a research proposal within the quarterly submission windows, and they will just convert it. So you're not required to wait a year to get a real research proposal. In fact, they prefer if you do the transition as soon as possible. But you do have a year. Because sometimes people do have to spend time with the XSEDE support staff to get their code up to speed or whatever it is. It takes time. Or, it used to work well on their computer, but not on those computers. And they may, after a few months, they may decide to move you to another computer that's more suitable. Because either you apply to the wrong computer because it's your first time, or, after the fact, they discover it's not the right computer. They really do give that year for some cases like that, but usually within 2-3 months you're done, you're ready.
If you have unused resources, does that affect positively or negatively your allocation from previous point?
Officially, there's no rule about that, but unofficially, yes. They don't like to see unused cycles. In fact, they will give you a small advance. Small, like maybe about 5% of what you asked for. If you run out of time and you just keep running, they'll let you run for another 5% towards the end of your allocation. And then, of course, they'll deduct it from next year's. So they really do want to use the cycles. And you should really use all the cycles you're given. Otherwise, it kind of, the next round, they'll take that into account, right?
So for that startup, how many times I can apply for the allocation?
You can, technically speaking, a PI can only apply for a startup once. You're supposed to just figure out your situation within 12 months.
So if I use all my time in a startup, then I submit the proposal, but I didn't get that, for example, then how can I do for the next time for the different project? Is it possible to get another one?
In principle, you cannot get another startup. In practice, the XSEDE people are reasonable people. So if you talk to them, they may be able to help you out. It does happen. It's not very common, but it happens. But they don't, it's not the official thing. They have the right to say no, basically. But generally, they try to help you if they see that you're trying, it's your first time. They really try to get people on board, which is part of the problem, right? They get so oversubscribed. I mean, their mandate is to get everybody computing. So everybody starts computing, and then the computer isn't big enough. Yes?
Is there any funding tied to this in any way? Can you ever submit joint proposals with other sort of funding grants and things like that? Or it's always just computing time only?
Yeah, XSEDE is computing time and free access to people's brains. I described to you a research proposal that has a single PI. You can write multi-PI research proposals for very large, much larger chunks of time. But there's no money. There are supercomputing grants which there is money. For example, the NSF PRAC, which is for the big ones. But the money is only for travel. It's for you to travel to the yearly conference where you say what you did to everybody else who's getting the same grant, and for you to go to NCSA for intense software development with the local experts. Like maybe 10,000 over 2 years or something. Just travel money. There's no money. And they explicitly say any money you might get cannot be used to support people. Yeah. I want to tell you one more thing so you can understand some of the frustrations in the land of computing with the NSF and also the DOE and all these, but the NSF especially. Officially, these computers are supposed to support research that is funded by the NSF, although you are not required to have an NSF grant to apply for XSEDE. For the DOE, if you want to get DOE computing time, you have to have a grant from the DOE. No matter how small, you have to have one. NSF, you're not officially required. But this is officially the computational infrastructure that's supposed to support NSF computational work. It's for free, right? So sometimes if you write a regular NSF grant and you ask for money for computers, the reviewers say, why should we give you money? Because we already got XSEDE. And then you're like, yeah, but I can't run anything there that's big, right? Because I run out of hours. There's no solution to this problem, right? Other than them making the computers bigger, but there's limits to what they can do. If they're 3 times oversubscribed, right? They're not going to get a computer 3 times bigger in the next 5 years. It's just not going to happen. I mean, all across the board. So I just want to tell you of some of the frustrations you might run into. But definitely apply for this if it seems appropriate to you, and definitely apply for a trial or a startup just to get your feet wet. Most of them are standard Linux-like computers, so you're probably familiar with the interface to some extent. You have to figure out where the libraries are and stuff. It's relatively straightforward. The web pages are quite good for XSEDE supercomputers, relatively complete documentation. You can always ask the support specialist, and within a few hours they respond. There's an 800 number you can call to talk to somebody. Other questions? Yes?
You mentioned interface. Is it like Torque or LSF or?
Every computer has a different interface. Some of them use Torque, LSF, some other stuff. There's all kinds of names for these queuing systems. But almost every single one is a Unix-based prompt. I think there used to be a DOS one at Cornell a few years ago, but that's gone. Yeah, Microsoft basically forced Cornell to buy buy hardware from them and to use Windows for supercomputing. It did not work out very well. Yeah, it looks very familiar to you logging in. You can even go through a website and do SSH through a website. You don't need a terminal. They have all kinds of tools like that if you're interested in that. You have to get some kind of a digital key pass. These days are very common. The equivalent of a physical dongle in the old days you plug into your computer. Now it's usually through a piece of software on your phone. You get a double authentication like we do at Yale. Pretty standard stuff, nothing too complicated. Other questions? So let's look at the yearly cycles. So for the research submissions, these are the windows. So they start on April 1st, July 1st, October 1st, and January 1st. It's 4 times a year, so you can't be too far off. And they tell you the answer like within a month before it starts. They're pretty prompt. They don't run late like other government agencies that evaluate regular grants. Sometimes you have no idea when they're going to review the thing, right, or when their panels meet. But these people are serious about it. Like when they say July 1st, you're going to know the answer by June 20th. Rain or shine. Maybe you get cut, but you know the answer. Okay. That's all I have to say.